Hello everyone, and I hope you all had a very Merry Christmas. And in this video, what I want to investigate is the integral over all real numbers of cosine of x divided by x squared plus 1 to the n, with respect to x, of course. Let's get complex analysising. Note that cosine of x is equal to the real part of e to the xi. And substituting this in and rearranging a little bit, we see that our integral, which I will just call I for brevity, is just equal to the real part of the integral over all real numbers of e to the xi divided by x squared plus 1 to the n, and then with respect to x, of course. And what we're going to do is integrate this function right here, so our integrand right here, integrate that. I feel like blue would be a better choice. We're going to integrate this right here around our usual semicircular contour. So we have this right here, and you'll see we have a single pole at x equals I. So our integral, this bit right here, is equal to 2 pi I times, well, the sum of the residues. But we only have one residue, so it's going to be equal to 2 pi I times the residue of this function at I. And what is the residue of this function at I? Well, just using the formula, we see that our residue at I is just equal to, I'll zoom in a little bit, is equal to, well, 1 over n minus 1, because the degree, n minus 1 factorial, because you see that the degree of this right here, of our pole, is going to be n, because we can split up this x squared plus 1 into x plus I, x minus I, and then all that to the n, right? So then that means we have the n minus 1th derivative, nth minus 1 derivative, which we will be dealing with, don't worry, of, well, e to the xi, and then times x minus I to the n over x squared plus 1 to the n. But as I said, we can just factor this bit right here. So we factor the denominator into x plus I to the n, x minus I to the n. So these right here just cancel. And what we're left with is just e to the xi over x plus I all to the n. And there's a limit here. So now this is just a matter of evaluating this right here, this nth derivative, and that right there will be our integral. And this is really quite interesting. And to evaluate it, I want to consider an adjacent nth derivative, and then from that we'll figure this out. Consider for a moment the mth derivative of x to the n times e to the x. Let's consider what this is right here. Well, the 0th derivative is obvious, but the first derivative is what? So we'll just do a list of derivatives right here. So the first derivative, this right here would be, well, it's just going to be product rule, right? So we have x to the n, and then times e to the x, and then plus nx n minus 1 times e to the x. And factoring out e to the x times n minus 1, or e to the x times x to the n minus 1, it's a mouthful. What we end up getting is x to the n minus 1, e to the x, and then times x, and then plus n. Okay, what about the second derivative? Well, we just have to differentiate what we just got from the first derivative, right? So we'll just do product rule, but like 3 times this time, right? So we're going to end up with n minus 1 times x to the n minus 2 now, times e to the x, and then x plus n, and then plus x to the n minus 1 times e to the x, because, you know, the derivative of e to the x is just e to the x, and then we have, oh, not equals, plus one more time. Well, the derivative of x plus n is just going to be 1, because the coefficient from the x is just 1, so we just have an x to the n minus 1 times e to the x. And let's go ahead and factor out an e to the x times x to the n minus 2, and let's see what we get there. So this right here is all equal to x to the n minus 2 times e to the x. And then, well, for our first term, we have an n minus 1, so we have times x plus n, x plus n. And then we have plus x times x plus n. And then for this last one, we're just going to have plus an x itself. And let's foil out what this is right here. Let's let's try to get get this into terms of like a normal quadratic, right? So distributing this n times n minus 1, we find that this is an distributing the n minus 1. We have an n times n minus 1, and then plus n minus 1 times x. But then we also have another x term, or two other x terms, really, because this is an n right here. Distributing this over this next term, we have a plus nx, and then we have a plus x squared, and then plus an x. And this is all a mouthful, and it's quite long, but this does simplify a little bit. This minus 1 here and this x are going to cancel because it's just minus x plus x, right? Leaving us with nx plus nx, which is just 2nx. So we have x squared plus 2nx, and then plus n minus 1 times n. And you might be able to start seeing a pattern right here. Perhaps it is just me in hindsight being like, yes, there's obviously a pattern here. But let's do it one more time, and hopefully that will reveal the actual pattern and what's going on here. So the third derivative, so we need to differentiate this quadratic, right? And we had an x to the n minus 2 times e to the x. So we need to differentiate all that right there. So doing the usual triple product rule, we have an n minus 2 e to the x, and then times our quadratic here, so x squared plus 2nx plus n minus 1. And then we have plus, well, derivative of e to the x is just e to the x. We have x to the n. I didn't write the, that's funny. There should be an x to the n minus 3 here. I do apologize. Plus x to the n minus 2 e to the x, and then x squared plus 2nx plus n minus 1 times n, and then plus one more row, plus the derivative of what's inside of our quadratic there. So we just have plus x to the n minus 2 e to the x, and then what's that, 2x, and then plus 2n. So what on earth does this give us? Let's go ahead and factor out an e to the x times x to the n minus 3, and let's see what that gives us. So then we have e to the x to the n minus 3. And what does our first term become? Well, that's just going to be an n minus 2 times our quadratic. So x squared plus 2nx plus n minus 1. What's our next term? Well, our next term is just going to be, well, x times our quadratic. So x squared plus 2nx times, or sorry, plus n minus 1. And then our next one is just going on to another line. Our next one is just going to be x times 2x plus 2n. And now what we need to do is just group our terms, right? Let's go ahead and try to figure out what the coefficient for x cubed is going to be, x squared, x, and then our constant term, right? And hopefully that will reveal the pattern that's occurring here. So our only term for x cubed is going to be this right here, where we have an x times an x squared. That's the only thing that's happening there. So in terms of this this polynomial, I'll scroll down here. In terms of the polynomial, we just have an x cubed right there. Okay, what about x squared? What about all of our terms for this x squared term? Well, we see that we have an n minus 2 x squared right here. So we have x squared, then we have n minus 2, right? But then what other x squared terms do we have? Well, we see we're distributing this x right here to this right here. So that means we have a 2nx squared, so plus 2n right here. And then right here, we're going to have one more, where we just have a 2x squared, right? So we're just going to have a plus 2. And you'll see here that a lot of the stuff cancels, or half of it at least. We have plus 2 minus 2, right? So we just get rid of those. And then we have an n plus 2n, so that's just going to be 3n. So we have 3nx squared. And then what about the next one? What about our coefficient for x? Well, for x, we're just going to have 2n times n minus 2. So 2n n minus 2. And then we have over here an n minus 1 because we're distributing that x again. So we have plus n minus 1 times n. And then right here we're going to have a 2n as well. 2n. And simplifying this term right here, if we factor out an n real fast, we see that we get 2 times n minus 2, so that's going to be 2 minus 2n minus 4, and then plus n minus 1, and then plus 2, right? And you'll see that we can group these terms again, right? We have negative 4, or we have 2 minus 4 minus 1, which is just negative 3, and then we have 2n plus n, which is just 3n. So we really have an n times 3n minus 3, but we can just factor that out, factor out a 3 to get 3 times n, n minus 1. So that term right there is just going to be 3n times n minus 1. So I'm going to erase all this real fast just for the sake of space and keeping everything compact. So now we have 3n and then n minus 1. Okay, and then this last constant term, well, the only term that's going to be constant is going to be this term right here, where we're distributing this right here, because every other term has a random x, and I say random, it's a calculated x, it has an x in front of it. So we have a plus n times n minus 1, and then n minus 2. And you'll see here that there is a certain pattern starting to emerge, that being that we have a binomial coefficient in front of each term, right? So here we have 1, 3, 3, 1, right? But then in the previous one, we had 1, 2, 1, and in the first one, we had just, well, 1, I guess. It was 1, 1. But you'll see that it does follow that pattern of binomial coefficients. But it's not just binomial coefficients, you'll see. It's binomial coefficients plus the fact that we have all these n's right here. So we start with no n on the cubed term, then we have a 3, then we have an n. Then we have an n times n minus 1, and then you have an n times n minus 1 times n minus 2. And the pattern for that is going to just be a falling factorial. So we can write this into a general rule. You see that for the nth derivative we take, to get this polynomial, we end up factoring out an e to the x times x to the n minus, well, whatever degree derivative we're taking, right? So for example, in this third one, we differentiated 3 times, and we have an x to the n minus 3 out front, right? So generalizing this to the following rule, we can postulate that the nth derivative of x to the n times e to the x is equal to e to the x times x to the n minus m, and then times, well, the following, well, we really don't need parentheses because we're going to have a sum. The sum from k equals 0 all the way up to m of, well, you see that we have an x to the k, obviously. We have a power there. But then we also have our binomial coefficients, right? So we're going to have m and then choose k. But then you'll also see that we have our extra n's here. And the way we're going to take care of those in our rule is going to be by the following factorial. So we're going to have n, and then there's the following factorial n, and then m minus k. The way these following factorials are defined is, for example, we have an x, and then following factorial of 0, right? That right there is just going to be 1. But if we have x following factorial of, say, 1, right, that's just going to be equal to x. And you'll see here that this kind of applies. This does apply here. So, for example, if we take m to be 3 and k to be 0, you see that we have n following factorial 3 minus 0, which is going to be 3. So we have n times n minus 1 times n minus 2, which makes sense, right? And then if you plug in m, right, so n0, you end up with just a 1, which is what we see with the x cubed term right there. So it does follow so far. And the way we're going to prove this is actually by induction. So the base case, you could kind of check for, well, we'll set real fast, I guess. I mean, if you plug in m equals 0 right here, well, we're summing from k equals 0 to 0, so we just plug in 0 into here, right? And we end up with, I mean, let's just see, that's 1 because, you know, you have x to the 0, that's just 1, right? M is 0 and k is 0, So 0 to 0, well, that's just going to be 1 because 0 factorial is just 1, right? So that's 1. And then this right here, as we've already discussed, that's just going to be 1 right there. So all that's 1. M is 0, so this right here is just x to the n. So there's no reason to worry about the m term, or the m right there. So it does indeed satisfy the base case right there. And the way we're going to do this by induction is by differentiating all of this right here one more time and, rearranging it or simplifying it to get what we expect. So differentiating this right here, we have d over dx. For the sake of simplicity, I'm going to throw all the x's together, so times the sum. So e to the x times the sum from k equals 0 to infinity of x to the n minus m plus k. And then m choose k, and then n following factorial m minus k. Okay, and what we're going to do here is just apply our good old product rule, right? So e to the x, derivative of that is going to be, I should close parentheses, e to the x. So we have e to the x times our big sum right here. So our sum from k equals 0 to m, that's an m, of x to the n minus m plus k. M choose k, and then n following factorial m minus k. And then we have to differentiate our x right here. So we have plus e to the x, and then let's see, this will be inside the sum. So sum from k equals 0 to infinity of x, or really n minus m plus k, times x to the n minus m plus k minus 1, and then m k, and then n m minus k. And you'll see here, it naturally follows. No, I'm kidding. Not. I don't think you can just take one look at this and be like, yes, of course. This, it follows that. You can just that's just the next term in the sequence. We do have to do a bit of simplifying here. So the way we're going to simplify this, to start at least, is going to be by factoring out e to the x times x to the n minus k minus 1. Minus m minus 1. So that will make dealing with our sums just a little bit easier. So we have e to the, that's a very long e, that's kind of weird. So we have e to the x, and then x to the n minus m minus 1. And then that means inside of those parentheses, we're going to have sum from k equals 0 to m of x to the k, and then m choose k, n m minus k, and then plus our sum from k equals 0 to m of x to the k minus 1, and then m choose k. And then let's actually take a look at this following factorial term right here. The definition for the following factorial, as I already said, but written out a bit more succinctly perhaps, is that n choose like x right here. This right here is going to be equal to n times n minus 1 dot 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 n minus x plus 1. Which means that if we multiply it by, say, the next term, like this right here, so we have an n minus m plus k. If we multiply this by an n minus x, right? If we multiply this by an n minus x on both sides, an n minus x, you'll see that this right here is now just the following factorial, but for n and then x minus 1. Or pardon me, this would be an x plus 1. So given that, we see that we have an n minus m plus k right here, which is, and you'll see that the minus part right here, this right here is the negative of that. So we can actually just rewrite this following factorial term, and instead of just n following factorial m minus k, we can just rewrite this as, well, n following factorial m minus k, and then plus 1. We can rewrite it as that, just to simplify things a little bit. I do apologize, there was a slight error. This right here, this x should have been x to the k plus 1. And also this sum should not have been from k equals 0 to infinity, though it actually would have made a difference because the binomial coefficient is 0 for k is greater than m. But at any rate, apologies for the mistakes. But what we can do now to simplify is to re-index this right here, because you see we have an x to the k plus 1, and it would be nice to just get all of our x's just to the k, right? So we can re-index this, right? We can say this is now the sum from k equals 1 to m plus 1 now of x to the k, and then times m choose k minus 1, and then following factorial n, and then m minus k minus, plus 1. And you'll see that we have something very similar here, but the thing that's keeping us from combining them is the fact that this is a sum from k equals 0 to m, and this is a sum from k equals 0 to m. It doesn't help if I point at the screen if you can't see me pointing. Yeah, that's kind of funny. Anyway, sum from k equals 0 to m right here, and we have a sum from k equals 1 to m plus 1 there. So let's consider if just extending our bounds, right? Let's make this now a sum from k equals 1, or sorry, from k equals 0 to m plus 1, right? And what's going to be our extra term that we have to subtract? Well, when we plug in k equals 0 to all this, we end up finding that, well, the x term just becomes a 1, but we have an m choose negative 1. And that's just always going to be 0. So it doesn't matter if we index this from k equals 1 or k equals 0. The 0th term right there, for k equals 0, that term is just 0. So we can index that from k. And actually the exact same thing goes for this sum right here, for our second sum. Because whenever we plug in m plus 1 right here, m plus 1 is obviously greater than just m, meaning that this binomial coefficient really just takes care of the term and makes it 0. So this right here is all just, we could combine into one big lump sum. And now we have plus x to the k, m choose k, and then n following factorial, m minus k plus 1. And you'll see that we can factor out the x to the k, and then n following factorial m minus k plus 1, right? So what that leaves us with is the sum right here from k equals 0 to m plus 1, x to the k, and then n following factorial m minus m plus 1 minus k. I'll write it like that because you'll hopefully see why shortly. And then we have times m choose k minus 1, and then plus m choose k. I will leave it as a proof to the viewer to prove that this right here is indeed m plus 1 choose k. I'm writing a paper at the moment about that Galton board, and I do prove it in the paper. I'll probably end up posting the paper on a community tab on the channel as well. So the proof will hopefully be on the channel somewhere in the near future. But for now, that's going to be a proof left to the reader, because that just, I feel like just for the sake of brevity, it's better just to leave that as that. So now bring down this e to the e term. It's e to the x times x to the n minus m minus 1. So this right here is just going to be our sum total. It's just going to be, see I did there, sum total. E to the x times x to the n minus m minus 1 times our sum from k equals 0 to m plus 1, and then times x to the k, m plus 1 choose k, and then n, and then following factorial m plus 1 minus k. And you'll see here that this is indeed what we would get in our formula. So take a look at that. Scrolling up here, you'll see that this right here is the exact same thing if we were to replace m with m plus 1 in this formula right here. So by induction, this is true, meaning that we have a formula for the mth derivative of this right here. So how on earth does that apply to our integral right here? Well, you'll see that we have the n minus 1th derivative of this right here. And that means we can evaluate that. So using our formula for the mth derivative of x to the n times e to the x, we can now evaluate this expression right here. The way we're going to begin simplifying this is going to be to try to match this right here, our nth derivative, or our general formula, with this right here, what we actually want or need to calculate to evaluate our integral. We see that this x plus I is equivalent to our x right here in terms of like what's being raised to the n or minus n power. And there really is no issue substituting or switching between the two. And the reason for that is because, well, first off, our values, this formula will work for negative values of n because the power rule still does apply, right? If you differentiate x squared the same as you would differentiate x to the minus 2, right? And then the second thing is that there is no extra coefficient in front of the x. So there is no additional chain rule going on here. Just the derivative of x plus I is just the same as the derivative of just x. They're both 1. That means that we can just convert, or really insert this x plus I right here to the minus n into our formula with no issue. But what does cause an issue is this right here, the argument of our exponential, this xi right here, because you see that in our formula, we're differentiating completely with respect to the variable that's being raised, that e is being raised to, right? So we're differentiating with respect to x, and we have an e to the x. There's no additional I there. So the way we're going to get around this actually is just by introducing do u substitution, rather ironically. We're going to let u equal x times I. And this is going to do a couple of things. First off, it's going to let us express this term right here as e to the u, but you'll notice that we're still differentiating with respect to x. We're differentiating with respect to x n minus 1 times. So one way we can get around this is by multiplying, kind of quote unquote, by du's, by these differentials, n minus 1 times. And we can group them, right? We can just switch these two in the denominator. So that way we're differentiating with respect to u, and then we have just du n minus 1 over dx n minus 1. So actually writing that out. So now we need to do a couple of things. First off, we need to convert this now into being in terms of u, and that's really not that big of an issue because, well, we see that x is equal to u over I, right? So you just kind of do a bit of surgery here, and we just rewrite this as u over I plus I. But you see that that kind of violates our whole thing with the we don't want an extra coefficient there to deal with chain rule. So we can just multiply the top and bottom of all this by I to the minus n. So an I to the minus n. And you see that if we just take the top one and distribute it, it cancels with the u and gives us a minus 1, right? So erasing this, this is now 1. 1 and then u minus 1 because I times I is just negative 1. So now I have u minus 1 to the minus n. And everything is basically good. We have, we're differentiating with respect to u, and we only have u's. But we do have this right here, this du over dx to the n minus 1. But we know that u over x is just equal to I. So that right there is literally just I to the n minus 1, right? And we also have this I right here. So in total, that becomes I to the 2n minus 1. And then times the n minus 1th derivative with respect to u of this right here, u minus 1 to the minus n, and then e to the u. And this right here, we can just use our formula to evaluate because there's no issue putting in a u minus 1 in here because, again, no extra chain rule needs to be applied, right? So using our formula, we find the following. This right here is what you obtain whenever you apply this formula right here that we derived. And you plug in m is equal to n minus 1 because that's how many times we're differentiating. And you replace all the x's being raised to a certain power with u minus 1s, right? And one more thing we need to do is take the limit as x approaches I, or in other words, because x approaches I, u is going to approach negative 1. So we can just plug in negative 1 into this formula and see what we get. We're going to have I out front, so I to the 2n minus 1. That there's not going to change. But then we have this minus 1, so minus 2 to the 1 minus 2n power. And then we have our e to just the minus 1. And then we have our sum from k equals 0 to n minus 1, and then minus 2 to just the k. and then m choose k. And then we have this rather interesting term right here. We have our negative n and then a following factorial with it. This following factorial can be rewritten instead of minus n and then as an argument right there, we can make that a positive n actually by making this a rising factorial and throwing in a negative 1 and then to the n minus 1 minus k. I will leave a link in the description to a proof, or well, the wiki page for this at least. But this is going to equal negative 1 to the n minus 1 minus k, and then times n, and then a rising factorial n minus 1 minus k. And that's going off the screen. And now that we have this, we can really just go ahead and really just start simplifying a lot of things and expressing some things in terms of factorials and the like. So what we're going to start with is actually just going to be this rising factorial. One way we can write this right here. I apologize, this should be n minus 1 right here. N minus 1. One way we can evaluate this right here, this rising factorial, is just by the following formula. We have n and then plus n minus 1. So 2n and then minus 1, and then minus k, minus 1 again. So it's really this minus 2 factorial, and then divided by this factorial minus 1, so n minus 1 factorial. And now expanding out our binomial coefficients, we see that we have n minus 1 factorial on the numerator over k factorial, and then n minus k factorial. I'm not going to simplify these or these. I don't think those can be simplified. But what can be completely canceled is this right here with that. Those just cancel. And we also have this minus 2 to the 1 minus n, 2n minus, plus k. And I'm just bringing in all the terms from the outside just to get one negative 2 term. And then we also have our sum. So we have our sum from k equals 0 to n minus 1. And then we have our, well, negative 1 to the n over I times e. And this right here, you may remember, is just going to be our residue. This is our residue at I. But you'll remember that our total integral is going to be 2 pi I times the sum times the residue, right? And I do apologize, actually. I am just remembering I left out a factor of 1 over n minus 1 factorial right here. And the reason for that is because it just comes from the formula for a residue. But we have 2 pi I times some of our residues. So multiplying this by 2 pi I. So adding in our negative 1 term, this negative 1 to the n minus 1 minus k, we find that our total integral, multiplying by 2 pi I, is going to be the following. You will see that the I in the 2 pi I and the I in the denominator will just cancel, leaving us with 2 pi over e. Now, the interesting thing here is that we can simplify this even further, actually. And the reason for that is because you see here that we have this minus 1 to the n. So right here we have this minus 1 to the n. But we also have another minus 1 to the n right here. And one thing we can do is just combine these terms. So we can say that we now have just 1 and then 2 right here. And you'll see that the exponent right here is the exact same thing, but just negative of the exponent right here. And what that means is that because it's just negative 1, we can just drop that term and then drop the negative inside of the 2 right there, meaning that we can just have 2 raised to the power of that and then drop the negative 1 to make things a lot simpler. And that right there, ladies and gentlemen, is our answer. That is the value of our integral. One of my favorite integrals actually is the integral from 0 to infinity of cosine of x over x squared plus 1. So just to kind of spot check this and see that this actually does work, we can plug in n equals 1 and see what we get, just to make sure we do get pi over e, which is the answer there. So if we say, I'll just in a different color, if we let n equal 1, that means k must be 0 because our sum is going from 0 to 0, right? Plugging all this in, we see that we have 2 pi over e and then 1 over n minus 1 factorial, but that's just 0 factorial. So that's just 1, which is nice. But inside our sum, we have, let's see, 2 to the 1 minus 2 plus 0. So 2 to the minus 1, which is just 1/2. And then times, let's see, 2 minus 2 minus 0, and then 0 factorial, and then 1 minus 0. So that all right there is just 1, meaning we have that term right there is just a half. So we do end up getting this pi over e. This was a longer video than I originally intended, but I found it awfully fun to record, and I hope all of you enjoyed, and I hope you all have a very happy new year, and thank you all for watching, and I'll see you in the next one.